Jeff is a professor of soil science and reclamation, specialist for West Virginia University. He received his PhD from Texas A&M University and his MS and BS from Brigham Young University. Jeff has more than 40 years of experience in coal mining and land reclamation. He teaches courses in soil and soil analysis, and oil and gas site reclamation, revegetation of disturbed lands, and remediating contaminated soils, and water reforestation, native plant restoration, which is great, and other opportunities. So I'm gonna bring Jeff up and let him get started.
Thank you.
Yep.
So,
Oh.
so before I start, I want to make sure that you know that this next spring we will be sponsoring our regular task force meeting in April, but we have decided to include a group called the International Mine Water Association. So this is a big group. I've been to their meeting a couple of times. I went to New Zealand 2 years ago and to Wales last year, and it's a great group. We've got 30 countries that are going to be represented, and that's just the start of it. We have about 100 abstracts already, so it'll be a week-long meeting, 3 or 4 concurrent sessions. We've got a mid-conference, I'm supposed to show you these other, here's all the different topics, 4 days of concurrent sessions, and of course we'll have sponsors and exhibitors, and we have 4 workshops set up right now. We have these 5 mid-conference field trips. I'll be leading a couple of them, and Ed was just here. He's going to lead one, bring some of the group up to Pennsylvania. So again, my intent is here we've got an international group that in general are not near as far along in applied projects as we are here. And so I'm encouraging people to dust off their old presentations that are classics and come and present them. You don't have to write a paper, so just come and present and let the world know what we are doing here. So I'm hopeful that that's the kind of thing that you can do. So you can go to our task force website if you're familiar with that. It'll take you through, you just click on, and then you'll get the regular site. So I hope you'll come. I've got some reminders here that if you're interested in that, but I hope that you'll consider coming. It's at a nice venue down in Morgantown. All right, so today what I want to talk about is some of the early discoveries, and believe it or not, I got to West Virginia in the early 1980s. It's really getting close. I've been at WVU for 38 years. That is one of the first things I learned. I was learning a lot in those early days about hydrology and mining, and that's of course when we started with the passive treatment system with Kleinman and the group at the Bureau of Mines in Pittsburgh. So anyway, I want to talk about that. Look at the group down there: Bob Hedden, Bob Kleinman, Bob Nairn, who's at Oklahoma, all good friends, Tom Wildman, and of course Jim Gusick. Many of you probably know all of those people. So, all right, so what I want to answer today is how did it begin? What were the sort of original ideas that circulated around that? Who were some of the players? And then what were those processes that were discovered and when? So let's see if you can pass a quiz. Remember, I'm a university professor, so I expect you to know something. So which ones are true and false? So do passage treatment systems work in these situations where no power is available? Okay, generally, especially that's when it started out. The site is remote, high flow, and low to moderate acidity. All right, well, in the early days, not high flow, man. We never thought that we could deal with big flows. Where active treatment is too expensive, absolutely, that's what we kind of developed it for. Only used on abandoned sites? No, we've certainly expanded. No regulatory effluent limit is specified. Well, that's what it originally was started out, because we didn't know what kind of effluent limits we could make. We didn't know what the effluent quality was going to be. only a one-time installation? Well, originally, that's what we thought. We were gonna put these wetlands in, and then we would be able to walk from them for 10 or 20 years. And some have been that way, haven't they? No funds were available for daily, yes, and any system will work in all conditions. No, of course not. So here's our false statements there that we are, I hope that you would have already gotten. All right, so we published a paper, now it's gotten almost 5 years ago, 6 years ago, that I, at the time, was kind of the top paper, or at least the one that gave the most current information. And so in that, I want to just describe some of these. So today we have the biological ones that we categorize them in, and the biochemical or geochemical. And so we'll hit just the original 4 or 5 that were the most important. So anyway, this is, I want to describe for you how, from my perspective, how it began. When I gave a version of this paper in Wales last year, I had a bunch of those international people coming up to me and saying, well, you know, we thought of this back then, and nobody knew. Well, we didn't know because we weren't talking to each other, and they had some of the same ideas. So it was one of those sort of things when it was the right time, is a right time topic for people to discover. And so these things were going on in a lot of different places too. So the earliest wetlands, as you probably know, were municipal systems where they either captured just runoff from parking lots and other places where they just tried to get some of the sediment out, or maybe even oil and grease from some place. I did some early work on looking at constructed wetlands for municipal systems and for individual homes. And so again, that was the idea of these wetlands were filter systems, mostly for sediment, and maybe a couple of other pollutants. Here's some of the stuff I worked on in the mid-1980s, where we had these microcosms, or these cattle troughs of wetland, where we were putting different substrates in them and different plants. And we would run different quality of water through them, trying to figure out what were the important criteria for them to work. So we had them all piped up with, some of them received acid mine drainage, some received water, some received other things. And then we had different substrates in them. We learned a lot from that experiment. Here are the 2 classic books that I remember reading and nearly memorizing in those days, from 1989, Old Hammer and it's Moshiri in 94. But here's the business about mine water. So the first paper that we ever saw on this was a presentation made by this Brent Huntsman in 1978. And what they saw over in Ohio was this area that had a big old bog here, and there was a little bit of acid mine drainage going through it, and it came out better on the other end. And they were just amazed. In fact, all of us were. And we didn't know really why that was the case. Were the plants doing something? Was it all cation exchange with the substrates? Was there limestone in it somewhere? And it turned out that all of those were the case, but they didn't know it at the time. They didn't know what the mechanisms were, why the water was working. So we've seen that. A lot of people have seen bad water going through natural wetlands and the water coming out on the end, but we also wondered what's happening to this ecosystem in the wetland. And do they turn into iron ponds? Do they just become deaf? And again, depending on what the flow and how bad the load is. Here's one of the ones, the first ones I saw over in Maryland. I went over with a guy named Marty Ravenhorse, and we were looking at wetlands, and he showed me this one that had acid mine drainage in it, and it was coming out on the other side clearer. And so we started measuring that and started thinking about how to do that. So again, this was not an individual observation. Paul Eager, a good friend, in 1980 saw that some of this metal was removed by a sphagnum bog. Weeder was probably the first guy in West Virginia that saw that. Kel's a pretty good friend. Anyway, and you get the idea that this phenomenon was happening in several places. And you can see the years that this was going on. Of course, that's someone finally said, well, why are we degrading our natural wetlands? Why don't we start building ones that are actually built for mine drainage? And so, again, those are the old days when you didn't carry a phone around. The only time you saw each other was at a meeting, maybe if you went to the same one. So there just wasn't the kind of communication that you would have expected. And things were going on in different places so that you didn't know. So here's the kind of the first thing that happened. So Kleinman went and saw that meeting in Ohio at the Geological Society meeting. And that's when he started talking to those guys at Wright State University in Dayton, or close to Dayton. And so with their help, Bob and his group at the U.S. Bureau of Mines built this thing called a porta-bog. So it's a flatbed trailer. He had these little runners along the side, so he would pull them up to an AMD seat, and he'd get the water up into this, and then he'd run back and forth, looking for retention time, and then measuring the water quality along that. Pretty clever, eh? Of course, it'd get sloshed around when you tried to move it, and so that didn't last very long. But that was one of the first attempts at trying to understand what was happening along the length of a wetland that was built. So that some of his first publication on this was in 1985. So you can see the sequence of things that are happening. So then we started building these wetlands on small seeps. And we very quickly saw that they could get overwhelmed with iron and getting crusted up and kill the plants. Sphagnum turned out to be not the most aggressive or tolerant of iron and acidity. And of course, that's when we switched over to some of the cattails. So they were much more tolerant of acid water than sphagnum. And again, some of that early work, then Pesavento, some of you knew he's a crazy guy. And then Snyder Nahara worked for Kleinman also. So again, there were a lot of ideas, a lot of people that were dealing with this. Some of them were crazier than others. So anyway, this was one of the first diagrams that we made on how to plant cattails. We weren't even really sure how well they would last, if they would last a long time. All right, so the next step, when we started seeing that, all right, we've got organic matter, we've got typha, and we can see that, there are organic reactions occurring. We were worried about not sending out so the pH would come up a little bit, but generally not that much. And it wasn't until some of the guys down in Tennessee found that when they had limestone associated with the wetlands, that the pH came up too, with a reduction in metals. And so that was the whole idea of not going to this anaerobic, or what we call a compost wetland, where we had limestone in the bottom, organic matter on the top. And so here's some of the early descriptions, pictures of how we started building those compost wetlands. We'd lay the limestone in the bottom, we'd put about 1 foot or 2 of organic matter on the surface. And again, we were a little bit confused about how deep the water should be. Should it be 1 or 2 or 3 inches deep? We finally got to the point where we didn't really want much water on the surface at all. We wanted the water to be moving kind of through the substrate, not across the surface. And so here's one of Bob's pictures where they put the organic matter and are planting the cattails. And so this was the typical design where you had this calcium carbonate with organic strata, and then the water level would change. This is a very early picture of some of my good old friends. And there's a very early picture of Bob Hedden when he was a youngster.
Wow.
Trish Erickson, good friend, worked for US EPA, and that's Michelle Gertz. So anyway, I think that's about a 1982 picture, 83 picture. So it's a long time ago. This was my first system in 1985, so we were all kind of got the idea, and I'd been talking to the Bureau of Mines people, and so I decided to build one on a small little clay mine, a Catanian clay mine that had bad water coming out of it, not much, 20 gallons a minute, aluminum and iron. And so I convinced the company to build this little thing. It had a 3-stage. We were trying to get something to happen here, and then started working through the organic matter with some limestone. worked great. In fact, it was there for about 25 years. And I've been by it and looked at it, and the thing continued to work, not as great as it did it early on, but when it was a low flow and not a great deal of acidity, it worked really great. So that was one of my first learning experiences, and of course we developed hundreds, if not thousands of them since then. I also started working with our state, West Virginia DEP, who took this on kind of as a big deal. We were trying to deal with abandoned discharges, bond forfeitures, and this was the only way we could deal with it then. So we did a lot of different types of systems. So this is one of the first ones we built in '87, and this one had a 6-cell system. You can see the top 3, and then the other 3 were down over the hill. Again, you can see what happens in these. So you get very nice color changes. Try to get it to have some residual time there, put baffles in it, try to get the water to run. This one worked again for a long, long time. And here it is, 16 years later, they evolve, and sometimes the cattails move up, sometimes it blows them out. But again, they tend to hang, they're pretty robust systems, again, if you just don't kill them with too much load. The next sort of idea, we thought that the plants were doing a lot, that somehow there was uptake of the metals and that, you know, that this biomass was contaminated. Well, we found out pretty early. A friend of mine, John Sinkendiver, and I began looking at the biomass and whether there was much metal increases in those things, and it turns out there really wasn't. They are able to tolerate those metals, but they exclude them. So the metals are mostly attaching to the organic matter, attaching to the roots and substrate. The plants generally are not taking up very much. And so that was an important point to realize. And it was about that time when one of my microbiologists got interested in these slimes and the microbial content of the substrate. And so this is Alan Sexton, long retired, but we began looking at that along with a number of other people. And so these oily sheens were sort of indicative of some of the microorganism stuff that was going on. So we all know that stinky smell, that hydrogen sulfide smell, and in any wetland, if it's working very well, you'll have that stinky smell there because that means that you've got anaerobic conditions, you've got anaerobic microbes working and converting sulfate back to sulfide, a reduction process. So anyway, we just began designing so many of these things, some with plants, some without them, some with limestone, some without. And in that process, we learned a lot. I published, honestly, dozens of papers on different systems with different constraints, and of course, so is everybody else. And I can remember a 1988 meeting in Pittsburgh where there were probably, honestly, 60 or 80 papers of that conference that were on passive systems, why they worked, why they didn't work, with all the constraints. All right, so the next thing that we started looking at, Zinkavich and I, Paul Zinkavich at WVU, and I began worrying about this armoring problem. And so everybody's always assumed that once the iron gets, kind of armored up or coated, that the limestone quits dissolving. And so we started measuring some of those armored limestone areas, and we found out that we still got a little bit of treatment. That was a shock to us. And so we started looking and building these open channels that were going to get armored, and we looked at how they dissolve. We did a bunch of lab work also. And what we found was that once you armor up the limestone, it goes down about, it only reacts about 20%. So you lose a lot. You lose 80% of your reaction simply because your surface area is coated up. But we also found out that there's still a little bit of dissolution that occurs, and really the armoring just slows that down. And so you just need to think about building these open channels longer, like 5 times, 20%, 5 times longer. and you can get similar treatment. And of course, what's really great is if you can get them blasted out and have a lot of surface water come through them on a slope, and that'll clean off some of that line, some of that pollution. All right, the next great idea that was done by these guys at Turner and McCoy down in 1990 was this idea of an anoxic limestone drain. The way they discovered it is they had some acid mine drainage going under a railroad bed that was limestone. And when it would come out, it would come out clear, the pH would be really high, and then within 20 or 30 feet, bang, it would turn red, pH would drop, and it was a classic chemistry experiment of anaerobic limestone raising the pH to 6.4, ferrous iron, it wouldn't coat, and then as soon as it oxidized, suddenly you get the ferric iron, and then it starts coating everything. That was a revelation. I can still remember sitting in the audience listening to Crazy Turner say this, and I thought, I've got it. And so we started this idea of building anoxic limestone drains, catching the water anaerobically under the ground, running it through a bed of limestone, and then having it come out, pH 6.4, clear, and then as soon as it oxidized, you had to have a pond to capture all the iron. Because the iron was conservative. It went through the limestone and didn't coat it. Boy, that was a cool idea. So we built a lot of those things. I still think anoxic drains are great things, but they are really, really finicky and they're fussy. And you got to make sure that you get the right water for the right system. If you can't get it anaerobic and you've got a little bit of iron in it, it'll start coating up that iron. If it's not and it's working, it'll smell bad and it'll turn black. And that's exactly what you want because the microbes are there. Which you can still see the limestone. It's still fresh. This is what often happens. I've often told people anoxic limestone drains are always failing. It just depends on the rate, and like a third of them fail within the first year because the guys screwed up putting them in. The next third fail in the next 5 or 6 years, just simply because things go wrong, and then the last third end up working for 10 or 15 or 20 years. And probably all of you have seen all of those situations. So this is what we don't want. Clogs up the limestone, blows out the top, and then you have to start over. I thought, and DEP and I decided, well, can't we try and treat that water a little bit by putting in some organic matter? And so our first effort was to put here's our sort of our anoxic limestone drain. We thought, well, maybe if we put some organic matter in, that'll suck up a little of that oxygen so that it'll make them last a little longer. So we stuck hay bales on the top of them, wrapped them up, and it sure didn't work. It turned into a big old microbial mat and still blew out the top. So that was a bad idea. It didn't work. But then that's when our other friends kind of came up, how can we pre-treat the water so that we can send it into an ALD? Of course, that's how the SAPs, or the vertical flow wetlands, then came about. Old Kettler and Cleary in 1994. We built ones that were horizontal, but they were very clever in building this drainage pipe in the bottom, driving the water down through the organic matter, and then running it into an ALD, and then keeping the water level based on, the outflow pipe. Very clever. I was really proud of them. And we had them come and build a bunch of those, and everybody's built vertical flow wetlands. Remember, they were initially called SAPs, successive alkaline producing systems. So those have been built all over the place. I've got to admit, I'm not a great fan of them. They are pretty. You got to have the right water for those things too, because they tend to rat hole down through the organic matter. There's a lot of little functional, physical problems that can go wrong with these systems. But boy, when they work, they really work great. All right, so here's a SAPS, or a vertical flow wetland. Here's the drainage system in the bottom, 3 or 4 feet of limestone. It can be coarse or fine. Coarser because you really want void space to keep the water moving. lay the organic matter over the top, put the water 2 or 3 feet above it, because you're trying to drive that water down through the organic matter, through the limestone, through that drainage system and out. And that's getting close. And so people put lots of drainage pipes to maintain drainage. And we've looked at how much we really do flush out in those systems, and sometimes it's not much. All right, then I think this is about the last one. The last really good idea, how we doing?
No, you're good.
Oh, and that was the open limestone channel. Paul and I, when we thought about those clogging pores, that 20% number tended to be pretty good, and so we just needed to build open limestone channels. Again, early 1990s is when we kind of put that all together. So you can see over that 10-year period of about 1985 to 1995, man, oh man, we were just trying all sorts of different things, and by observation and just simple trial and error, we were learning so much. And so this is the original sort of decision chart for the passive systems. We only had 3 things. We had the aerobic wetlands, we had the compost limestone wetlands, and then we had the anoxic limestone drains. And that's all we had. And we didn't know any different. And of course, today, this was in 1994 that Hidden and Kleinman published. So we had a few more because we had the open limestone channel and the saps that had been added on. And so this was by 1994. Some of you may remember that. And again, the design criteria based on dissolved oxygen, how much iron and aluminum you could take in, because each of those were treated differently. And so that was the 5 choices in 1994. And then I guess the next one was this whole idea of bioreactors, this idea of microbial, how that influences water quality. And so that was really started by some of the people out in Colorado with metal mines. Again, they had much slower, smaller flows, they had much longer retention times, and that's what you really have to have with microbial treatment. You gotta make that water slow down, sit there for a long time, and then the microbes can work on it. So this was some of the stuff they did at the Big 5 tunnel. I went out there, and Jim Gusick and Tom showed me around that place. And sulfate reduction is a process that's really important and really tends to help metals become sulfides. And so some of this, again, was done in Pittsburgh. McIntyre and Edenborn were with Kleinman's group, but Tom did a lot of that early work. All right, so today, and I think this is even outdated now after 5 or 6 years, we have these, what I call 12 choices, and I think we could probably expand that even now. So we have the biological ones, and you probably can figure out the coding here: aerobic, anaerobic, the vertical flow wetlands, and the sulfate reducing bioreactors. So again, those are the ones that are slow, that you need sulfate reduction to occur. So that's the biological ones. And then here's all the ones that have some sort of geochemical limestone dissolution. So whether it's a manganese reducing bed, an anoxic drain, a limestone leach bed, you all know that one, where you can flush the limestone through it. What's even better, I set up a system in New Zealand once where we tried to capture fresh water, run it through limestone, and then run that sort of charged water into an AMD stream. It's pretty good, except you don't generate much alkalinity with fresh water. Limestone dissolves very poorly. But, again, if you've got a big load, or a lot of flow, you can get alkalinity out. So anyway, and of course, I didn't tell you about slag. We found that slag would work pretty well as an alkaline charging solution. But lush limestone leach beds, low pH channels, the open limestone channels, limestone sand, and diversion wells. So anyway, it's been really quite a fun thing. So here's my summary statements. And so when appropriately designed, passive systems can provide long-term, again, depending on some criteria, efficient and effective treatment again, we've had some that have worked for 20 years, 25 years. And of course, you have to renovate them in some way. Passive treatment really relies on natural processes to neutralize acidity and reciprocal metals. It's most suitable for small to moderate flows. And again, there have been people that have put them on really big flows now. And again, there's sometimes a hybrid system where there's a little bit of an active component to it. So the appropriate chemistry, biological uses organic matter, microbes. Geochemical systems are usually limestone or some alkalinity source, whether it's slag. And then most of these do employ more than just one wetland. It's multiple techniques or multiple systems. And then flow and acidity and alkalinity, those are things you have to monitor up front to help you design your system. There's a lot of people that know how to design these things based on those criteria. So again, I think all of you could answer this. In general, passive systems work best on those lower flows. If we get much above 100 gallons per minute, that's when I start thinking, boy, I don't know whether we can do it. And this low to moderate acidity, and again, 500 milligrams per liter acidity is about my limit. That gives you about 20 to 30, maybe 40 iron, 10 aluminum. If you get much above any of those metal concentrations, you've got to come up with some alternative things to do. And they don't work well if the flow's too high, if the metals are too great, or the acidity is too high. Again, nothing new that we need to do. So there they are again. So there's the discovery order. So aerobic, the anaerobic, the anoxic drains, open limestone channels, vertical flow wetlands, and then these sulfate reducing bioreactors. So again, you can kind of think of that as a short time frame, but at the time, holy cow, we were just busting our heads trying to figure out why some were working better in these different situations. And when we didn't talk to each other, it was a hobnob of a lot of things going on. So what's next in passive systems? I hope you'll come to my meeting, because we'll have a lot of the international people that are going to be bringing these kinds of ideas. And again, we've developed into multiple big systems with lots of different techniques, whether you start out with an aerobic settling pond that goes into a SAPS or a vertical flow wetland, then into an open limestone channel. There are multiple methods that are being used. And this is one of Bob Nairn's down at Tar Creek, Oklahoma. So I could talk more about some other ones, but anyway, that's probably a good place to stop. And
We have just a few couple minutes for questions.
okay.
Anybody have questions? Go ahead.
Have you done any studies looking at potential differences of species of vegetation in these wetlands, and if there were differences in the success of the system?
Yeah, that seems to still be one of the not so well studied, because I don't know that it matters that much based on the other things that go on in these kind of systems. So if I were to, that would be not my priority to try to study. And really, is there mixed systems that would do better? There's an ecosystem there. But honestly, we have found that sphagnum doesn't last very long in these things. Cattails do. And even if you have some of those other components, the cattails just take over. Yeah.
In the systems that have failed, has there been any look to quantify, like, were they used in the wrong situation with the wrong water and stuff like that? Is there been a lot of look into that, and see why they fell?
Yeah, there's been a lot of that work. And of course, people don't like to report that so much. They'd rather talk about, this one really worked great, and this is why. But often we can figure out pretty quickly, and it does tend to be substrate related, what happened with the pore space, and the fact that nothing can dissolve or work. Once the cation exchange capacity of the organic matter or the material that's in there, once it gets saturated, boy, you just pretty much have to take that out and put some new new material in. So that's usually what it is. It's just that, you know, it's been there long enough, it's aged, evolved, and its capacity to absorb or take up metals has been exhausted.
Perfect timing.
All right.
Thank
Who
you,
wants
Jeff.
one of my little forms? Right away.
Maria.